So this is a talk about why should we write code or codes when we can write code or codes that themselves write codes, question mark. We're at Pi Gotham. It's Saturday, October 5th, 2019. I'm James. If you like this talk, you can follow me on Twitter. I give a lot of goofy talks every year, and so this is just one of them. We have to go really fast because we've only got about 25 minutes to cover a lot of material. So this is our general agenda. We'll do a little bit of review. We'll go through some motivations, and we'll talk about general techniques for automatically generating code. Let's start with our review. Now, the purpose of this review is just to make sure that we have a common baseline, a common understanding of how certain things work in Python. So you have a function here in Python. It just adds two numbers together, x and y. You run this function. It adds them together. It prints out the output. Nothing too special. When you do that, let's do that. Let's get the jitters out. OK. When you do that, what actually happens behind the scenes is Python takes this source code, it turns it into bytecode, and it actually executes the bytecode. And the bytecode looks something like this. In the case of adding two numbers together, you're loading two local variables, and you're doing a binary add operation, and that's pretty much all that's happening there. What actually happens beyond just that, beyond the writing of the bytecode, is Python takes this source code on disk, it transforms that into an AST. The AST looks something like this. Well, maybe not something like this, but maybe something like this. And you can see here's the definition of the module that is actually contains this function. You can see the definition of the function f. Once it creates that AST, what it does with that AST is it actually goes and it tries to generate bytecode from that AST. There's a lot of extra steps in between, like generating a symbol table, constant folding, peephole optimization. But effectively, what you end up with is a code object looks like this. That's not particularly useful to look at, so maybe something that looks like that. The bytecode is literally just a set of bytes that tell the Python interpreter what to do. That itself is not particularly useful to look at. So you can think the bytecodes are actually just single byte numeric values representing what the operation the Python interpreter should do. And maybe the best way to look at that would be something like this. You can see this is, again, our function that loads two constant values, creates a function that itself just swaps two variables and returns a value. Now, if we think about that, and we want to go a little bit deeper, we can think, how does this actually work within Python? And so the most naive understanding of how this might work is there's some mechanism within the Python interpreter that looks at all the bytecodes and runs through the bytecodes one by one, executing them. And this is actually almost exactly what we see in CPython itself. Here's a CPython source code. This is a file called ceval.c. Within ceval.c, there's literally a main loop that has an infinite for loop. Within that infinite for loop, there's a switch statement that determines what the bytecode should do. For example, for the binary add, you can see this is the actual operation for performing an addition in Python. When performing an addition in Python, what you'll see is that there is some abstract representation of the underlying protocol. Here, this is called PyNumber add. PyNumber add doesn't necessarily mean adding two numbers, but it means adding two things as though they were numbers. If you were to dispatch to this PyNumber add, you can see this handles all the conceptual addition in Python. And so, for example, you can see if you're adding two sequences here, you might actually perform a concatenation if they're strings or if they're lists. But if you're not performing this addition operation on two things that are sequences, you might then go dispatch further. If they happen to be something like integers or longs, you might actually end up dispatching to something that looks like this, long add. And this is the underlying code that actually takes you from x plus y in Python all the way to, at the machine level, taking two integers, adding them together, automatically promoting, and handling all of those details. And this is something that you can prove to yourself very easily. It's something that's very easy to see. If we took just this code here, and we ran it under our debugger, and we put a breakpoint on that long add, and we looked at the backtrace for this, we'd see all the pieces that I showed you. You'd see the long add right up here. You'd see the PyNumber in-place add in this particular case here. And you'd see the PyEval framex. That's the loop that runs forever, evaluating each individual bytecode. And in fact, if this happened to be something a little bit deeper, like a function that called a function that called a function, you'll see that PyEval frame loop occur multiple times. So if we run this under our debugger, and we put a backtrace on it, you'll see this PyEval framex appear multiple times, one for each frame. So this PyEval framex, this interpretation of the bytecode happens at each level, at each function that's being processed by Python. Now, if you happen to have something that is a little bit more complicated, like you're importing a module. In Python, I do a lot of Python trainings, and as part of the advanced training, one of the things we do is we try and mock out how Python actually works behind the scenes. We try and mock out what happens when you import a module. Here's a very simple example of what happens when you actually go and import a module for the first time in Python. What Python will actually do is it'll see, have I imported this module before? If I've imported this module before, just return the value that I imported before out of sys.modules. If I haven't, go find it through some mechanism. There's actually a very complex mechanism you can hook into. It used to be called import hooks, and now it's part of a larger import mechanism. It goes and it finds a file, probably some file with a py extension. It opens that file, it reads the source text out of that file, it parses that source text like we saw to generate the AST, it compiles that into bytecode, it executes that in some namespace, and it returns that namespace to you. And so when you do something like from numpy import linalg, you're actually just doing an object lookup on this object that was created through this process. Now, this is something of a simplification. There ends up being a lot of additional hook points in here. For example, you can hook point into not only, there's actually a lot of more mechanisms here. You can hook into not only how the module is found, how the module is decoded, because you can think you're reading some source from disk. And so if you look at some of the crazy things that people do with embedding other languages into Python, like Joe Jevnik's quasi-quotes project, he uses the encoding mechanism in order to take some code that is itself not valid Python, give it a fake encoder. That encoder then takes out the parts that aren't valid Python and then transpiles them to something that he can actually build into a Python bytecode stream. If you look at something like the building of a class, and we have some simple class T, it has a function f, and that's all it's there. That also has its own mechanism behind it. When you build a class, it's just a mechanism that's followed by Python, that's followed at runtime. So you have some namespace, you have the class body, all the stuff that sits under the namespace, you execute it, and then you get the class definition. Now, this is actually something of a lie. This is not actually what happens. What really happens is a lot uglier. What you do is you take the body of the function, you put it into another function, you execute that function to build a class body, and you do this at runtime. You do that within a namespace so that and that namespace itself can be hooked into using mechanisms like prepare, and then you provide that off to the end user. And so it would end up looking something like this. I put a ... here because I really couldn't be bothered last night to finish writing this. The mechanism itself is a lot more complicated than that. But fundamentally, what you want to get from this is that it is just a mechanism. It's a runtime mechanism. It's just a step of processes that take you from some code in some file that you're editing in a text editor to something that runs. So that's basically where we want to start with our review. But before we get into the techniques that you do for code generation, let's talk slightly about the motivation for why you'd want to do some kind of automatic code generation. And I didn't want to overthink what these motivations are, so I think probably the most valid one is you're a programmer, you're bored at work. And if you don't happen to be a programmer and you happen to be a manager, maybe just as importantly, your programmers who work for you are bored at work. And it's probably important to keep them engaged in what they're doing. And so I think that's a sufficient motivation here. Why are they bored at work? They're bored at work because they're writing a lot of really repetitive code, and that can be very boring. And maybe they've even heard somewhere along the way, don't repeat yourself. I don't like this phrase that much because I feel like when people try to avoid repeating themselves, they end up writing abstractions that don't quite solve a problem. I think a better way to look at why you'd write why you do automatic code generation is not about not repeating yourselves, but it's more about normalization. And so when this topic of normalization comes up in, say, the database community, it really focuses on two major areas. One, reducing the sizing of an encoding. In the case of automatic code generation, this would be reducing the amount of boilerplate that you have to sit there and spend hours typing out when it's the same thing over and over. And two, and more importantly, eliminating update anomalies. I think it is the desire to eliminate update anomalies that drives many of the abstractions that we see in the programming languages that we use. And so let's talk a little bit about what an update anomaly is. If you have perhaps two functions, and those functions both have to operate in some fashion in some context where they need some authorization or authentication. You might have a little bit of code that looks like this. If this is an active account and if this user is an authorized user, then you do some work. And you have another function G that has to do some other work. And so in adding this authorization authentication behavior to G, you might find that you have a duplication here. The huge risk here is what if the mechanism by which you determine whether a user is authenticated or authorized slightly changes? Then you'll have an update anomaly because you'll change F, but G won't change automatically, and part of your code base will be correct and the other part of your code base will be incorrect. And the typical approach that we use to solve this is we extract this to a separate function and we call that function in both places. And in Python, we have even nicer features available to us. We can put this into a decorator, and you see this all the time when you're doing web programming and something like Flask. You just make sure that your views ensure that the user is authenticated. Now, when you talk about update anomalies, I think what's important or what's interesting to look at when you talk about update anomalies is the pattern of the code that you're trying to eliminate this update anomaly for. For example, a very simple pattern that we saw here was just common functionality. You had two functions, they have some common functionality. You need to make sure when you update one, the other one gets updated correspondingly. So you extract this into a function or a module. Just basic modularity is what you do here. Now, in Python, you have the ability to be a little bit more specific. There's a very rich set of features that you can use in order to avoid update anomalies. For example, what if that pattern of the thing that you're trying to make sure updates in sync happens to be always occurring before or after, like you're always doing a check before, you're always checking the user authenticated before, or something that you're doing with a result value, and you're always wrapping them the same way, then you probably would use a decorator in Python. Similarly, if your pattern were that you are extending some functionality, like you have something that you need to wrap and you need to do one small, tiny little change to it, and maybe it's not really extending functionality, but something that you might call a protocol, then you might use the data model in Python, or more specifically, you might use something like inheritance in Python, and that would be the mechanism by which you avoid these update anomalies. It turns out that you have a lot of choices for avoiding update anomalies in Python. Code generation is just one of them. And the choice of which one you choose may be influenced by factors beyond just what kind of update or what the pattern is. They may be influenced by factors like you want nice looking syntax, or influenced by factors like you're working with another API and that API needs to take a callable in a particular form or a class in a particular form, or you might just believe in the rule of threes. I'm glad people got that joke. So let's talk broadly. Let's now dive into broadly the kind of techniques that we see when we talk about automatic code generation. We've done enough editorializing. Oftentimes people talk about code generation as a metaprogramming approach. Metaprogramming is a very underspecified term. In Python, it comes to mean a lot of different things. And let's talk a little bit about how they are. But before we go into examples of how you might do metaprogramming in Python, let's try to classify them in some way. I find that most approaches about metaprogramming in Python fall into about 4 general categories. One of them is you're using some built-in functionality. Python gives you some ability to do some metaprogramming, either by its inherent dynamic nature or by some feature that is provided to you. Otherwise, you're hooking into some built-in functionality. Python gives you the ability, for example, to create a class, and you put some hooks into that. Python gives you the ability to import a module. You put a hook into what it means to import a module. Python gives you the ability to, for example, evaluate bytecode. And it turns out that a PEP was accepted about 5 years ago to allow you to customize the bytecode interpreter for Python so that you can add JITs to CPython very easily. Fortunately, the JITting never really happened. Another example would be that you want to construct something dynamically. So you find some mechanism by which you construct one of these Pythonic structures dynamically. And it turns out that there are many different layers at which you can construct something dynamically. And so when you look at these 4 categories, they're not really strict delineations. It's not necessarily that one of the metaprogramming approaches is only one of these, but they usually fit into one of these buckets. And so when we talk about metaprogramming approaches in the last few minutes we have for this talk, I'll show you, you'll see how they fit into these buckets. Now, one of the things I don't want to do, not just because I don't have any time, but because it's kind of stupid, is I don't want to talk about the pros and the cons of each metaprogramming approach. I know that just sounds really boring, but instead I'll give you a couple of techniques that you can use yourself after this talk is over to evaluate whether these are approaches that you want to use. One very important one is, can a normal human being understand what's going on here? Another would be, does this metaprogramming approach, does this code generation approach comport with the tools that we use? Bear in mind that most of the tools that we're currently using for authoring code are static. They're tools like grep. Think about this. You give a new code base. You're told you need to extend this code base, add some functionality. You need to find where to add that functionality. The first thing you're going to do is you're going to grep through that code base. But grep works on source code on disk. And so if that happens to be some function that you need to extend that was generated by some runtime mechanism, you'll grep all day long. You'll never be able to find it. And so many of these approaches comport very poorly with static analysis techniques or with the static tooling that we use. And we still live in a very static world. The dream of image systems, the scheme dream of everything lives in some runtime enclosed image environment never actually happened. Another evaluation might be, what is the organizational hierarchy of the authors of this code? For example, if you exist in an organization where there's a spectrum between library authors at the root and there are application authors at the leaves of the production of a particular product, a library author might provide some kind of mechanism for their library users, and it could be coercive or it could be cooperative in nature. They may be saying, look, I'll give you some mechanism to avoid update anomalies because I think you're going to get this wrong and I want to stop you from getting this wrong, or I think you're going to break you're going to pierce some veil that I've set up that makes it easy for me to refactor later, or you're doing it cooperatively. Oh, I'm giving you this code generation mechanism so it can make your life a little bit easier and can save you some time. Another consideration might be, does the code that you need to be generated runtime? Some of these mechanisms are very runtime generated mechanisms. Some of them are very compile time mechanism generated. When we talk about Python, we often talk about Python on the spectrum of being just an interpreted language. But if you really think about it, you can generally divide the time that you spend when you're writing code into 2 big buckets. Before you run it in production and after you run it in production, we can broadly call these runtime and compile time. One of the things is that when you're automatically generating code, does it need information that's only available in the field at runtime in production in order to automatically generate what it needs to work on? And if it doesn't, then maybe one of the approaches that you might want to use is something that can give you this statically generated code at compile time or build time. An important follow-up consideration is if you've been following any of the security transparency work, there have been 2 PEPs that have been put out. One of them has been accepted around security transparency. You may be existing in an environment where you're not able to generate code at runtime. For example, just imagine you are writing code for like a baseboard management controller. And so you're sitting in some data center, you have some little controller that sits on one of your servers. That controller is in a very privileged place because it can see all the network traffic. So it can do all sorts of crazy stuff to sniff the data that you have in your data center. You want to put some code on that baseboard management controller, you want to put some code on that BMC, and you want to lock down what code runs on that BMC so it's all code signed. This is what the security transparency PEPs are about, and those are mechanisms that will prevent you from automatically generating code at runtime that will work. These are mechanisms that are available in certain OSs. Windows 10, for example, has a feature called strict HVCI, hypervisor code integrity, which will prevent you from running automatically generated code at runtime, because that may be one mechanism by which a malware author will get into like a BMC and do something they're not supposed to do. Now, when you actually employ these code generation techniques, one of the things that you might think of as part of the way that you employ it is how well does the abstraction that you're using allow for customization. It's often the case when you're doing code generation, you have 10 things you want to automate, 10 pieces of code, 10 classes, 10 functions that all look mostly the same, except one of them looks a little bit different. And the question is, does the abstraction that you're choosing, does the technique that you're choosing allow you to do that little one that looks a little bit different? And similarly, does this mechanism preclude manual intervention? It's often the case that you want the code generation to be very routine for everything except that one little choice that's a little bit out. So with that said, let's go. Let's take a look at a couple of techniques. The first technique I said was you're using some built-in functionality. So let's say we have 2 functions here. They actually do most of the same thing. They're both binary functions, and the only difference here is the operation that they perform. And so a very simple functional programming approach that Python makes very easy for you, that even an intro Python programmer can do, is you extract this to You redefine this as a function that takes the operation. You inject this functionality of whether it's a exponentiation or whether it's an addition as a third argument that happens to be a method itself. And if you actually need to have a handle on f and g, you actually need to have a function called f and a function called g that are specialized to perform one of these operations together. Then you'll do something like this. You'll write a function that creates another function, and then you'll call that function on f and g, and you'll have one that this is the one that adds, and this is the one that pows. And you actually see this pattern quite often in Python. One of the places where you might see this pattern in Python is when you have a decorator that itself needs to generate another decorator. This is what we might call higher order decorators. So you have a simple decorator like this. It's just going to take the timing of something, but you want to specialize that decorator and add a little message at the top. And so you write this as a function that generates a decorator that then is applied to another function. It's a very, very common thing to see in Python. And this way, instead of having to write these 2 decorators as completely separate decorators, as 2 pieces of code, you unify that code base, and you have a function that creates a decorator, and then the decorator applies to those underlying functions and wraps them. It turns out that if you think about this a little bit more deeply, you can rewrite the code above for that decorator, something like this, just using a class. And if you think about it a little bit more deeply, you can see that these mechanisms by which you generate a function are very close in nature to the mechanisms by which you generate an instance of a class. It turns out that for a very long time, we've understood a certain duality in computer science between closures and objects. There are 2 sides of the same coin. And so this higher order decorator, this higher order function is really just another way to express the idea of a class that creates instances, or a way to specialize the behavior that is applied to a consistent set of state. So this is probably the most basic technique. There's quite a few more other techniques in Python. Let's take a look at the next layer of the hierarchy. For example, you're hooking into some functionality that's given to you in Python. For example, you're hooking into class construction. Historically, the biggest topic that people will talk about when they're talking about hooking into these mechanisms is hooking into class construction using a meta class. I gave a talk about 2 years ago that's got like 1 million hits on YouTube. Please don't look for it. But if anything came out of that talk, it's that people understand why metaclasses are actually useful. It's a very narrow use case, mostly around, for example, it's mostly around asserting constraints from a base class to a derived class. But effectively, the code kind of looks like this. You're hooking into what happens when Python needs to create a class. And so in this case, you're saying, I'm creating a class. If that class happens to have a method called f, I'm going to wrap that method and add a little print statement at the top, and then I'm going to continue on in the class construction process. And so when you apply this meta class to a and b, these methods f here and here print something extra when you actually run them. Now, it turns out that this meta class approach is something that has been much ballyhooed. It is used in the Python standard library. abc.meta is one of the biggest examples of where you'll see the use of meta classes. The enum class is another use of meta classes, and effectively what these are both doing is enforcing some constraint from a base class to a derived class. In the case of ABC meta, that happens to be that you mark certain methods as abstract methods, and then in the derived classes, they must be implemented in order for that to be a valid derived class. This is a much ballyhooed method in Python because it turns out that it's just very difficult to get right, and there's a lot of sharp edges. There's an even sharper, even more powerful technique in Python using you can override a function in the built-ins called build class that intercepts all class construction. And so effectively in Python, it's kind of interesting. You could build your own object system completely parallel to the built-in Python object system with its own rules for inheritance, if you so desired, by hooking into build class. Maybe a slight, even within the meta class hierarchy, there's a lot more steps. You can define what the namespace in which the class is created with prepare. You can hook into the call. You can hook into the init. Probably what you should be doing if you want to apply this technique is to use something like init subclass, which was added fairly recently in Python 3.6. Init subclass is maybe a safe way in order to do this kind of hooking into class construction. It composes nicely. But fundamentally, one of the problems with all of these class construction hooks is you end up infecting the inheritance hierarchy. And so you end up maybe pushing too much onto the end users of this code. As a result, maybe a more popular approach that we see in Python in something like the data classes module is to have a class decorator. Here we have a class decorator that does exactly the same thing as above. You wrap a class, you see if it has a function, and you just amend that function by wrapping it. And so the end up code, the resulting code doesn't look that different. One of the major differences here, though, is you're looking at taking some functionality and pulling it purposefully rather than pushing it onto the people who derive from this. In other words, if you choose not to apply this wrapper, you don't push that functionality. Whereas in the meta class, what happens when a class is constructed is you determine the most derived meta class in order to construct that class. And so what that means is if you have a base class as a library author you're providing to your end users may be compelled to follow certain behaviors that the meta class constrains you to, the meta class guarantees as a result of this mechanism. Now, if you go a little bit deeper, I said the next step along the way would be something that looks like this. You're hooking into, or you're constructing something at a different level. So here you can see that Python actually gives you the ability to construct classes at runtime, not only by just typing them out at your interactive interpreter, but actually by using this type function. Many of you have probably already used a type function before in order to determine what the runtime type of something is. In this case, you can actually pass it arguments and construct a new type. And so here you have a function called create class, and it creates class of a certain name. And you fill in a couple extra details. So this create class function automatically gives you a new class, and it fills in a repr, and it gives you an extra function called f. And what you can see as a benefit of this is A and B are effectively going to be very similar looking if you were to write them out. Instead of writing them out in 6 lines total, you're writing them out in 2 lines, and you can begin to see where the differences might be a little bit more clearly. You're reducing a little bit of duplication, and you can see this is a way you can automatically generate these classes. Now, it turns out that you can do the exact same thing with the function, but it is really, really, really unpleasant. This is how you can create a function at runtime in Python. What you do is you go into the types module, you pull out the actual code type and the function type, and you figure out what the arguments are for the code type. Boy, there are a lot of arguments there, and for some reason, a lot of them are the number 2. But you can actually create a function at runtime by passing it the bytecode. So you can see here f and g are our functions from before, one that adds 2 numbers and one that multiplies 2 numbers. And I'm actually constructing them at runtime by just passing it the bytecode and having Python do this. This is actually a fairly safe mechanism. It's built into Python. It's well supported. It's something that you can do and you can do safely and it will be maintained. But in practice, probably the only places I've seen anybody do this latter is in either jokes or code transformers that happen to be jokes. Yeah. Now, the last technique I said is you can perform this construction on many different levels. I actually think probably one of the safest ways to do automatic code generation and one of the better ways to do automatic code generation is one of the most ballyhooed ways. It's the create a string and then exec the string. And people, for some reason, really seem to hate this, but it actually just works. And so here's an example of creating a function by literally taking a string, filling in some details, and execing that string. The upsides of this is you don't have to do this at runtime. You can have this function or this file run as part of your build process, so you can generate a physical artifact with the code that was generated so somebody can grep for it later. It ends up being quite amenable to people needing to add slight modifications or needing to diverge from the automation of this code generation. But for some reason, people really seem to hate this. And for many, many years, this is one of the techniques that was used behind collections.nametuple. Nametuple got a lot of flack for doing this. If you actually look at if you look at part of the standard library, you can see each one of these techniques are used at some point. This is collections.nametuple. The class decorator is dataclasses.dataclass. abc.meta is the use of an ABC, and it's only this kind of automatic class construction that is fairly rare to see in the standard library. I think you might I don't think I can think off the top of my head of any place you might see this in the standard library. So with that said, I think I'm exactly on time. That was a little talk about just some nuances and some details around why you might not write code when you can just write code that writes code. Thank you very much.